Question 2. Some oxides of elements in period 3 are shown. They are here. And then they are saying that sodium reacts with oxygen to form sodium oxide. Sodium is the reducing agent in this reaction. Define a reducing agent. A reducing agent is this species that donates electrons, because gaining of electrons is reduction. So if I give you what reduces you, then I'm the reducing agent. So is a species. This is a species that donates electrons. You can even say it gets oxidized. That means since it has lost electrons, it has given them out, then its electron, we call it the oxidation number, is going to increase. So for it becomes oxidized by losing of those electrons. Roman 2. Write an equation for the reaction of sodium oxide with water. Of course, when you get the oxide here and you add it in water, then you are going to get a hydroxide. So we shall get sodium hydroxide. So to balance this, since these are two sodiums, then I'll put 2 here. Oxygens are 2, hydrogens are 2, then hydrogens are also 2. So therefore, that is the equation there. Remember, it has to be balanced. If an equation is not balanced, then it is not correct. Aluminium oxide is an amphoteric oxide found in bauxite. Roman 1. State what is meant by amphoteric. This means that it can react with both acids and bases, or it shows both acidic and basic behavior. Okay, so amphoteric means able to react with both acids and bases. As simple as that. Then Roman 2, aluminium oxide is purified from bauxite in several steps. The first step involves heating aluminium oxide with an excess of sodium hydroxide. A colorless solution forms. Write an equation for this reaction. So this is the reaction of aluminium oxide with sodium hydroxide. Then we have to put water. And then what you get is sodium aluminate. Sodium aluminate. It is like this, with a 4 there. And then to balance this, aluminium here is 2. So I'll put a 2 here to balance the aluminium here. Then sodium hydroxide, sodium is 2 here, so I'll put a 2 here. And then hydrogens, this is 4 times 2. What is that? 8. Then here we have 2. That means these ones must be 6, so I'll put a 3 here to make this one a 6, and then a 2, giving us 8. Oxygen, this is 3 plus 2, 5 plus 3, 8. The same with this one here. So that is that. Roman 3, aluminium oxide is used as a catalyst in the dehydration of alcohols. And that is true, just as the same as concentrated sulfuric acid. Dehydrate alcohols to form alkenes. Okay. State the effect of using aluminium oxide as a catalyst in the dehydration of alcohols. Use the Boltzmann's distribution to help answer the question. Now, when you use a catalyst provides a pathway with the lower activation energy. So that means if I have, maybe this one here is the activation energy. When you use a catalyst, it has a lower activation energy. That means there are going to be many molecules that are going to have the energy to react. It is like when the pass mark, if the pass mark is, let's say you are doing a test and the pass mark is 70%, and you find that there are very few students who score this mark. You see that? Then maybe a teacher wants to choose how many students are going to take his subject, and says that the pass mark is going to be 70%, and gets one student who gets 70 and above. But there are people in 60s, but then he says, okay, I'm going to put the pass mark at 50%. Now you'll find that all the people who were in 50, 60, they were left out here. Now the number is going to increase. You see that? So that is what the catalyst does. Now it gives an opportunity to those particles that have gotten less energy compared to activation energy to react. So we shall have here, this will be the activation energy for the catalyst. So we put EA cat. Okay, so meaning you can see that there is now a greater proportion, okay, of molecules. Here the molecules are very few. But now look at the greater proportion here when the catalyst is there. So that means I will say greater proportion of molecules with their energy greater or equal to activation energy. So therefore, the frequency of effective collisions increases. Effective collisions increases, resulting into a higher rate of reaction. Okay, then part C, phosphorus oxide. This one here is a white solid that has a melting point of 24 degrees C. Then this solid here reacts with water to form phosphorus acid. Deduce the type of structure and bonding shown by this oxide here. Explain your answer. Now, the fact that this one has a melting point, which is 24 degrees C, room temperature, it is already a liquid. That means it already melted, okay? Because a liquid can come from the solid, and the solid has to melt to give you the liquid. Not so. So that means this one here has a simple all molecular. Sometimes we say simple molecular structure. Okay, simple molecular structure because of low melting point. Because of low melting point. That is the structure. Then the bonding, of course, it has to be covalent. So this is covalent bonding. Students always make a mistake here and they write convalent instead of covalent. They write conva. So please check that. Covalent bonding because it is hydrolyzed. Because it is easily hydrolyzed. Okay, hydrolysis has taken place. It reacts with water to form this. Ionic ones, for them, they just dissolve. They don't react with the water. The ions are just separated. Okay. Roman 2, determine the oxidation number of phosphorus in phosphorus acid. Now, hydrogen has the oxidation number of +1, or the oxidation state, so I will write, there are 3 of them, so times 1, then plus. For phosphorus, I don't know, so I give it N. And then oxygen, the oxidation state of every oxygen atom here is -2. Then I equate to 0 because this one has no charge, okay? Then 3 minus 6, that is a -3. So N minus 3 is equal to 0. Then take this one this side. It becomes a plus. So N is equal to +3. So that means here I'll write +3. Roman 3. When this oxide here is heated with oxygen, it forms this phosphorus pentaoxide, which actually dimerizes to give us the P4O10. Okay. Then here they are showing us the reaction here. The enthalpy change of reaction is a negative. That means this is an exothermic reaction. The enthalpy change of formation of this oxide here is negative 3012 kilojoules per mole. Calculate the enthalpy change of formation of this one here. So now what we are going to do, we are going to have what we call an energy diagram. I'm going to use the Hess's law. Okay, so we have oxygen here, and then we get this one as P4O10. Okay, actually the one I was talking about which polymerizes, yeah, actually it is this. It is coming from P2O5. So it it dimerizes, not polymerizing. So that is that. Okay, then these ones are all coming from phosphorus, then plus oxygen. Okay, these ones are 10, so I'll put a 5 here, then a 4 here, something like that. So these ones are formed from elements in their standard states. So this one is a gas, and this one is a solid. We form this one here, that is the enthalpy formation of this one here, which is negative 3012 kilojoules per mole. And then the enthalpy formation of this one, we don't know it, so I will put X here. The enthalpy formation of oxygen here, since this one is an element, its enthalpy formation is 0, so I leave it there. Using Hess's law, so it doesn't matter the steps, but what matters is the reactants and then the end product. So I can take this one like this. Okay, so I always say clockwise is equal to anti-clockwise. Okay, this one when it joins here, it joins that line. This one when it joins here, then it goes this other side. So we are going to have now X, then plus DHR here. Okay, the DHR is actually this one here, so we shall put plus minus 1372. Then this one is equal to this one here, which is minus 3012. So meaning X here is going to be equal to minus 3012. This one is a minus. When it crosses, it becomes a plus. So 1372. What do we get here? Negative 3012 plus 1372. We get negative 1640. Negative 1640. Write an equation for the reaction of this one with water. Of course, that phosphorus pentaoxide, when it reacts with water, we get phosphoric acid. So P4O10 plus water, we get phosphoric acid, which is H3, then PO4. To balance this one, we are going to look at now the number of phosphorus. So phosphorus atoms, we are seeing 4 here, and yet here we are having 1. So that means I can put a 4 here, meaning hydrogen is now 12. So if hydrogen is 12, then I will put a 6 here to balance that. How about oxygen? Oxygen is 6, then plus the 10, that is 16. Then 4 here times the 4, that is 16, so it's balanced. Remember, an equation must be balanced for it to be correct. Then D, sulfur dioxide and sulfur trioxide are found in the atmosphere. The oxidation of sulfur dioxide to sulfur trioxide in the atmosphere is catalyzed by nitrogen dioxide. Okay, then the first step of the catalytic oxidation is shown in this equation here. So how we can see that nitrogen here is losing an oxygen which is added to this, then you are seeing this, right? And then from there, construct an equation to show how nitrogen dioxide is regenerated in the catalytic oxidation. In catalysis, the catalyst may appear to be consumed at first, but then later it is regenerated. So here, what is going to happen that the nitrogen monoxide, which is formed here, reacts with oxygen readily available in the atmosphere, then to give us the nitrogen dioxide back. You see, to balance this one, these are 2 oxygens, and these ones are 3, So I may put a half here to make one oxygen and one oxygen there. So that is that. Then Roman 2, nitrogen dioxide can also react with unburned hydrocarbons to form photochemical smog. Okay, set the product of this reaction that contributes to the photochemical smog. That is what we call PAN. You can abbreviate it like this, or you can write it in full as peroxyacetyl nitrate. That is that. Roman 3, figure 2.2 shows how the temperature of the atmosphere varies with the height from the ground. So it is given like this, and then down here they are saying that the equilibrium reaction with equation 1 has DHR, the enthalpy of reaction, as negative 168 kilojoules per mole. Suggest how the position of this equilibrium differs at a height of 20 kilometers compared with the height of 50 kilometers from the ground. Explain your answer. Now, the first thing I will do is to come to this graph here, and then I look for 50, the height of 50, and then the one of 20. So 50 is here, kilometers. When I draw a line here, I even make it dotted. That is for the 50. Then I also extrapolate. I go down here, around there. Then I also make it dotted, like that. Then the one of 20, I do the same. Also down. Also make them dotted, just as the previous ones, like that. So we are seeing that at 50 degrees C, the temperature here is higher than this one here when it is at 20 degrees C. So the temperature is lower. And we are seeing that the enthalpy of, they say that the equilibrium reaction here has the DHR negative 168. So that means the forward reaction is exothermic, okay? Because this one is negative. So we say that suggest how the position of equilibrium differs at a height of 20 kilometers compared to the one of 50 kilometers above the ground. We shall see that the position of equilibrium actually shifts to the right because the forward reaction is exothermic. So at 20 kilometers, the temperature is colder. In fact, let me first tell you something here. The position of equilibrium at 50 kilometers. What are we seeing at 50 kilometers? It is here. Then we see the temperature is higher. So there is increase in the temperature. So if there is increase in the temperature and yet this one is an exothermic reaction, then that means that the position of equilibrium is going to shift to the left to favor the endothermic reaction, the endothermic side. Okay, so the position of equilibrium at 50 shifts to the left. Okay, shifts to the left. Why? Because the forward reaction is exothermic. The temperature at 50 kilometers is hotter. Okay, which favors the endothermic reaction. We can now say the position of equilibrium, so we can just write our answer as the position of equilibrium shifts to the right, okay, shifts to the right because shifts to the right at 20 kilometers. Why? Because the forward reaction is exothermic. Okay, is exothermic. How do you know? And the temperature at 20 kilometers is colder. You can say is lower. Okay, you can write this one or this one here. Okay, so at 20 kilometers, we can see that the temperature here is more colder than at 50 kilometers, which is now higher. So this being an exothermic reaction, at higher temperatures, you favor the backward reaction. And that backward reaction, okay, that one will be at 50. So the equilibrium will shift to the right, to the left at 50. At 20, it shifts to the right because the temperature is colder. Simple as that.